In this video, we're going to look at some familiar topics from a calculus perspective. What we're going to do first is start with a recall of some important vocabulary, the first of which is absolute extrema. And absolute extrema are the highest or lowest values that a function will take on over its entire domain. And we contrast that with what we call relative or local extrema. And relative extrema are function values that are higher or lower than all values nearby. And to clarify that, nearby to us will simply mean relative to location. Let's take a look at these concepts by making a quick graph. So I'll put a sharp point, a couple turning points here and here, and just make something similar on your own notes. And the first thing we'll look for is an absolute maximum, the absolute highest point that this function takes on, which is the fourth point that I've drawn in on the graph. We'll contrast that with the absolute minimum, the lowest point, which occurred at the far left endpoint for this graph. So an absolute max and an absolute min. As far as relative maximum, notice that we have two of those. We have 2 points that we say are higher or lower than everything nearby. One at the sharp point, and one that's also at the absolute maximum. And our relative minimum, well, we're only going to have one of those, right here about in the middle, the third point that I've drawn on the graph. And note, the two endpoints, even though they appear to be low points, we have no idea what happens on the other side of these points, to the left of the left endpoint and to the right of the right endpoint. And conceptually, relative extrema require a two-sided limit. That's the only way we can know if the values are higher or lower than everything nearby. So it must have a two-sided limit around these points. As opposed to absolute max and min, those can be endpoints. They don't require a two-sided limit. Relative extrema, no endpoints. And that brings us to the first big new concept in this video, the extreme value theorem. Which states that if f of x is a function that is continuous on a closed interval, we'll call it a to b, then f of x must have both an absolute maximum and an absolute minimum. If I make something that is continuous with defined endpoints, it will have an absolute highest point and an absolute lowest point. Even if the function's constant, that just means it's either all an absolute maximum or all an absolute minimum. So let's draw one more example with a curve that isn't on a closed interval, but with a curve on an open interval. So notice I drew in 2 turning points and a third point that's a sharp turning point. And so this function that we'll call f of x is shown with a domain that is all real numbers. Let's look for those extrema again. We'll say this first turning point, which I'm going to say happens at a value a, is a relative max. The second turning point at a value of b would be a relative minimum. And at this value c, we have another relative maximum. Well, the question to get us to our last big concept for this video is, What do you notice about the slope? Or think of the derivative at points A, B, and C, at these points where we had relative extrema. Well, notice at A, f prime of A would have to be 0. That is a moment where we flatten out and have a horizontal tangent line. Same thing at B. F prime of B is also 0. But notice at this last turning point, at this sharp point, well, f prime of C does not exist. This function is not differentiable at C. These 3 points that we are investigating on the graph are what are known as critical points. And critical points are points on a function where the derivative f prime is equal to 0 or the derivative does not exist. And the big takeaway from this will be that relative extrema for a function can only occur at critical points, which is a big note and one that's going to carry over into a lot of analysis that we do with derivatives in calculus. So what we'll finish up with is one final example. What we'll try to do is find x values for all critical points for the following function. F of x equals 4x cubed minus 3x squared plus 5. So if critical points are where the derivative equals 0 or is undefined, let's start by evaluating the derivative. F prime of x equals 12x squared minus 6x. Setting that equal to 0 and factoring, we get that 6x times the quantity 2x minus 1 equals 0, which gives our derivative zeros at x equals 0 and x equals 1/2. And so we're just going to set up a quick table to organize this information. Organizing the spots where the derivative was 0 on the left, again 0 and 1/2, and noting that on the right, the derivative does not exist. Well, we have none of those points. And that should be easy to recognize because our function and our subsequent derivative were both polynomials. They're continuous on the entire domain of real numbers. So that's it for this lesson, but this will get you prepared to start making further analysis using the first derivative. Thank you for watching.